You know that feeling, right? When a car takes off and you get pushed back into your seat? Well, today, we're going to break down the physics behind that exact feeling. We're talking about acceleration, what it is, how to picture it, and how to predict it with some seriously powerful equations.
So here's our game plan. We'll kick things off with what acceleration actually is. Then we'll see how graphs can make motion super easy to visualize. After that, we'll get into the three superstar equations of motion, use them to solve a real problem, and then we'll wrap it all up.
All right, let's jump right in. First things first, what in the world is acceleration?
Yeah, that sensation. The lurch forward when you brake, the push back when you hit the gas, that's it. That is literally acceleration in action. It's the physical feeling of your body reacting to a change in motion. And physics? Well, it gives us the language to describe it perfectly.
And here's the official definition. In physics, acceleration is just the rate of change of velocity. So, put simply, if your speed is changing, or even if just your direction is changing, congratulations, you are accelerating. It really is as simple as that.
And of course, there's a formula for it. A is our acceleration. All it is your final velocity, v, minus your initial velocity, u, divided by the time it took to make that change. This one little formula is basically the foundation for everything we're talking about today.
Now, acceleration can go two ways, positive or negative. If you're speeding up, that's positive acceleration. It's working with your direction of travel. But if you hit the brakes, that's negative acceleration. It's not a bad thing, it just means the force is working against your direction of motion to slow you down.
And it's also super important to get that acceleration isn't always a smooth, steady ride. Something falling through the air has uniform acceleration. It gets faster by the same amount every single second. But think about a car in traffic. That's the perfect example of non-uniform acceleration. You're spinning up, slowing down, stopping. Your velocity is just all over the map.
So, we've got the concept down. But how do we turn all these numbers into something we can understand in a single glance? Well, that's where graphs come in to save the day.
I mean, that's the big question, isn't it? How do we see the story of an object's journey? Graphs are the answer. They are basically the storyboard for motion.
Okay, let's start with a distance time graph. If you see a straight diagonal line, that's your clue that the object is cruising at a constant speed. But if that line starts to curve upwards, aha, that means it's covering more and more ground each second. In other words, it's accelerating.
But to really get a grip on acceleration, we're going to level up to a velocity time graph. These things are incredibly powerful. Not only do they show you an object's speed at any moment, but they have this awesome secret power. The area underneath the line tells you the total distance the object has traveled. How cool is that?
And this is where it all comes together beautifully. On a velocity time graph, a straight line that's sloped up or down means the velocity is changing by the same amount over time. And what do we call a steady change in velocity? You got it, uniform acceleration. And the steeper the line, the greater the acceleration. It's all right there in the picture.
So, we can define it, we can see it on a graph. Now it's time to pull out the physicist's ultimate toolkit for predicting motion.
Because, let's be honest, graphs are amazing for understanding, but you don't want to be sketching one out every time you need a precise calculation. We need something more direct. And that's exactly what the equations of motion are for.
Now here's the single most important rule to remember. These three equations are your new best friends, but they only work when you're dealing with uniform acceleration. If that acceleration is changing, these equations are off the table.
And here they are, the big three. The first one connects velocity and time, perfect for finding a future speed. The second one links position and time, so you can figure out how far something has gone. And the third one, it's a genius shortcut that connects position and velocity for when you don't even know the time. This is the whole shebang.
Okay, enough theory. It's time to put these equations to the test and solve a real-world problem.
So, let's imagine a car slamming on the brakes. The first thing we do is list everything we know. The acceleration is -6 because it's slowing down. It stops in 2 seconds, and its final velocity is 0. We take that, plug it into our first equation, and boom, we find out the car was originally going 12 meters per second. Now that we know that, we can use our second equation to solve for distance. And what do we get? The car traveled exactly 12 meters before stopping. See how they work together?
All right, let's bring this all home and make sure everything has clicked into place. So here are the three big takeaways. Number one, acceleration is just the rate of change of velocity. Speed up, slow down, change direction, it's all acceleration. Number two, Graphs are your secret weapon for visualizing motion. The slope and the area tell you almost everything. And 3, if you've got uniform acceleration, those 3 equations are your toolkit for predicting motion.
Okay, quick pop quiz. A bus slows down from 80 kilometers per hour to 60 in 5 seconds. Using what you know, what's its acceleration? And I'll give you a hint. Watch your units. You'll probably want to convert to meters per second first. And the answer is negative 1.11 meters per second squared. And that negative sign is the key. It's the math confirming what we already knew. The bus is slowing down. It's decelerating. Perfect. And this all brings us back to something incredibly practical. Our source material asks this great question. Now, can you appreciate why drivers are told to leave space on the road? It's because of physics. It takes time and distance to stop. This isn't just classroom theory. This is what keeps us safe.
So I'll leave you with a final thought. From throwing a ball to dropping your keys to a satellite whipping around the Earth, where else in your daily life can you spot these fundamental equations of motion at work? Once you start looking, you'll find they're absolutely everywhere.